Okay, last time I already introduced the eutectic reaction, right? And the eutectic composition, which can provide the highest mechanical property. For example, like the this team lab alloy phase diagram. So its eutectic reaction is at what? At 61.9 weight% of tin, right? And the what's the definition of eutectic reaction? So do you guys still remember that? The reaction at this composition. I mean, one liquefies, solidifies into two solids, right? Two solid. And on its left, it's called the hypoeutectic. Its right is hypereutectic. Okay, and when we heat up at say the 300 Celsius, and we keep cooling down, keep cooling down, and keep cooling down, and finally we'll get the layer structure with the core of alpha solid solution. Okay, if we heat up at 300 Celsius and keep cooling down to the say the 150, the cooling rate is very slow. We get the microstructure. It's like this. So we have an alpha solid solution core with the layer structure or lamella structure. Right? This structure, this this is the hypereutectic structure. Okay, so if the composition say is like 80 weight% of tin, 80 weight% of tin. So when we're cooling down, so what's the microstructure of hypereutectic is? Well, we just change the core from alpha to beta, okay, to beta. Okay? Therefore, we can find out its mechanical property corresponding to hypo or hypereutectic, right? Therefore, that's we already mentioned that the eutectic reaction is able to strengthen, can enhance this dispersion strengthening. Okay, therefore we find out that at this eutectic composition, for in this case, it's 61.9 of tin, right? We got the highest shear strength. And the microstructure of hypoeutectic is the alpha core with the lamella structure, and the hypereutectic reaction is the beta solid solution core with the lamella structure. Okay, and we can find the conclusions that the eutectic reaction at specific composition has the highest mechanical property, including the shear strength and the tensile strength. Okay, so on its left side of the eutectic reaction, that's the solid solution strength of alpha by tin initially at this point. Okay, and gradually the dispersion strengthening of alpha by beta for the hypereutectic reaction. Okay, so what's the definition of this point? What's the definition of this point? So this point is the UTS, ultimate tensile stress of pure tin. Okay, the same. And this point is the UTS of the pure lead metal. Okay, so from this result shows that this eutectic reaction provide the enhance the dispersion strengthening for the mechanical properties. Okay, so let's look at this figure. So I already talk about this experiment to find out this phase diagram, right? To plot this phase diagram, we have to run the experiment. So we mix this alloy with the specific composition and heat up to its liquidus line, liquidus temperature, and cooling down, right? We can get the figure like the left side, right? And we can map in the left side to the phase diagram, okay, to the phase diagram. Okay, so let's look at this experiment. We get this composition of, let's say, 30% of tin. Okay, that means we have like 70% of lead, right? And we just heat up to the melting temperature and cooling down. Okay, cooling down. And this point is the liquidus point, liquidus temperature here, right? And it can map into this point at the phase diagram. Okay. Okay, and below this temperature, the solid phase form. That's mean the alpha solid solution form. Okay, therefore for this region, it's two-phase region. Okay, it's two-phase region, and we can map in this point to here. Okay, okay, therefore we know. Okay, so the range from this point to this point is called the freezing range, right? It's called the freezing range. So if we have a higher freezing range, what's that mean for this alloy? What's the physical meaning of this alloy? If it has the higher range of the freezing range. Okay, that means this alloy has the higher latent heat. Okay, that means it needs longer time for phase transformation from liquid to solid. You get what I'm saying? Okay. Okay. And when this temperature keeps cooling below this this temperature is called the eutectic temperature below this point. Say here, it is completely solid. Okay, it's completely solid. Okay, it's completely solid. So at this point, because sorry, it's a reaction from transfer from the liquid to solid. Okay, it's the liquid phase in this two-phase region. You completely transfer or solidify into two solid phase. Okay, and below this point, say this point. So what's the microstructure of this point? I already discussed about this microstructure the previous slides. So it's a cone structure, right? It's a cone structure. It's a cone structure with lamella. Okay, therefore it's the cone structure. Okay, it's alpha with layer structure, right? Like this structure. Cone core structure of alpha solid solution with the lamella structure. So it's the alpha core with the eutectic. Okay, this the alpha is the core structure with the lamella structure or layer structure. Okay, so let me ask you a question. What's the figure of the temperature versus time for the eutectic reaction? So we already know that this point is the this is called the eutectic reaction, right? Right. So can you plot this eutectic reaction of this figure, from this figure. So what it should look like for this eutectic reaction? No, I'm sorry. For example, when I want to do the experiment to heat up to the liquidus point, right, liquidus temperature, and we find out when the temperature cooling down to a specific temperature, this liquid solidifies into two solid phase, right? So can you plot this figure of temperature versus time from this phase diagram? Or what this plot should be look like? What's this cooling curve? What's the cooling curve should be look like? Okay, it should be like this, right? Because there's no two-phase region. There's no two-phase region, right? This region is called two-phase region, right? Therefore, if we have the composition, say, 61.9% of tin, right? And we heat up at a 300, say 50, and cooling down specific temperature, right? When this temperature reached 183, which is the eutectic temperature, right? It will start to phase transformation. Okay, you have phase transformation. Okay. Okay, you go from the liquid to solid. Okay, liquid to solid. Okay, therefore we know that for the cooling curve, if this temperature remain, okay, if the temperature remain, okay, that's mean the eutectic reaction occur at this temperature, right? For this platinum, okay, for this platinum, that's mean this reaction occur. Okay, this reaction occur. Okay. And for the microstructure of eutectic reaction is completely the layer structure. Okay, layer by layer, alpha and beta, alpha, beta, without the core structure. Okay, without the core structure. Okay. So if we're from this this microscope, we can observe that for this hypoeutectic, right? Hypoeutectic, we can observe the structure is with the alpha core with the layer structure, right? And for this hypereutectic, its microstructure is beta core with the layer structure. Okay, and for this eutectic structure, it's completely layer structure. Okay, layer by layer, layer by layer. Okay. And for the eutectic reaction, the eutectic growth direction is depends on diffusion. Okay, it depends on the diffusion. Okay, so we already know for example, for the alpha solid solution, what's the matrix? What's the matrix? Okay, this is the alpha solid solution, right? Right, it's alpha solid solution. For this point, say you have 10% of tin. Therefore, we know that for the alpha solid solution, the matrix is lead, right? The matrix is lead metal. Okay, and the tin is used for the dispersion strengthening. Right? Therefore, this is for the dispersion strengthening. Dispersion strengthening. Okay, and for the beta phase, I mean the team is the matrix and that is for the dispersion strengthening. Okay, I mean in this case the team is the point defect for dispersion strengthening, and the beta solid solution that is the point defect for dispersion strengthening, and those point defect will diffuse from the surface. Okay, through the surface, it will keep diffuse and keep growth through the surface, layer by layer. Okay, to form this layer structure and lamella structure. And this figure is the microscope of the eutectic reaction, the eutectic structure. Okay. Okay, so let's look at the example of TeamLab eutectic reaction. Okay, say we have the 40 weight% of team, right? 40, so we know its initial composition is 40 at this point, right? And the temperature is about 150 Celsius, so 150 Celsius at this point, right? At this point, and determine the phase present. What's the phase present for this condition? We know the composition and temperature, right? I already mentioned that in previous chapters. We just need, initially we'll know the composition and temperature. Okay, so what's the phase present? So at this point, its phase is alpha plus beta, right? Alpha plus two solid phase. Okay, because this region is between the alpha and beta. And then we can draw a tie line, right? You remember that? And we get the intercept here and here. Okay. Therefore, we can find the phase composition is what? It's the composition of alpha solid solution is 11 weight% of tin, and the composition of what? Of beta solid solution is about 99 weight% of tin. Okay, therefore we can say it is its solubility. Okay, it is its solubility for this case. Okay, for this condition. Okay, for this condition, composition and temperature is its solubility. It's 11 weight% of tin and 99 weight% of tin. Okay, and the relative amount of each phase. So what's the relative amount of each phase? How many phases? Two solid phase, right? So do you remember if previously we determined these two phases as what? What's the two phases that we already taught before? It's liquid and solid, right? So for example, I got a composition and temperature at this point. Right? And then we can draw a tie line here, and we can get this composition of each phase, right? However, for this example, we have two solid phase. Therefore, we can find the weight fraction of alpha solid solution. We use the Lever's rule, right? Right. So how to find the weight fraction of alpha solid solution? We use this length as the what? Denominator, right? And use this fraction as the numerator. Okay, so we can get the weight fraction of alpha solid solution is 67 weight%. Therefore, the weight fraction of beta solid solution is 33 weight%. Okay, so we can use the Lever's rule that we already taught, okay, previously, right? So let's look at, so yeah, so that's the example that I already mentioned. If I get a condition, the same composition is 48% of tin, and the temperature is heat up at 220 Celsius, so we can find its phase is two phase, right? At this point, it's two phase. It's liquid and alpha, right? Liquid plus alpha. And we can get its composition. Phase composition is about the composition of the alpha solid solution is 17 weight% of tin, right? And the composition of the liquid is about 46 weight% of tin. Okay, therefore we can use the Lever's rule to figure out the weight fraction of alpha solid solution and the liquid, right? The same, use the Lever's rule, right? We can compare this lens to this lens to find out the weight fraction of alpha solid solution. Also, we can use this lens, the ratio of this lens to this lens to figure out the weight fraction of liquid phase, okay, of liquid phase. So let's do some a little summarize that the eutectic reaction. Okay, this eutectic reaction transformations to two solid phase, from one liquid to two solid. Okay, for the TeamLab system, its eutectic temperature is at 183 Celsius, with the composition 61.9 weight% of tin. And for the eutectoid reaction, if the one solid phase transforms to two other solid phase, that means we have one solid, and transfers to two solid. Okay, two solid. And for this for this system, TeamLab system, there's no eutectoid reaction presented. Okay, and for the protetic that I already mentioned, that is the liquid and one solid phase transferred to second solid phase. Okay, so one solid and liquid, one solid and liquid transfer to a second solid phase, Okay, so yeah. And the interlamellar spacing, the small spacing increases the strength of the eutectic, and the interlamellar spacing is determined by growth rate. Okay, determined by the growth rate. Well, this equation is from experiment. Okay, it's from this experiment. That's mean the growth rate of the lamellar structure, the eutectic structure. Okay, if the growth rate is higher, so how about the interlamellar spacing? So if the growth rate is higher, that means the interlamellar spacing is smaller. It's getting smaller, right? And the smaller spacing increases the strength of the eutectic structure. Okay. Therefore, if we want to improve this dispersion strengthening for this eutectic structure, so how can we do? We have to control the growth rate, right? One approach is to control the growth rate, okay, to facilitate the growth rate. And that can make the interlamellar spacing get smaller and smaller, okay? So the amount of eutectic, increase the stronger eutectic microconstitute, increases the alloy strength, right? So that's what we already mentioned, that the eutectic reaction improves this dispersion strengthening. Okay, in the microstructure of the eutectics can have the microstructure besides lamella, such as the needle-like flat plate. Okay, and addition of alloying elements can cause a modification of the microstructure, okay, such as needle-like platelets, and can be converted by dendrite growth into thin interconnected rods. This increases the tensile strength and the percent elongations. We already mentioned that the eutectic structure is one of the eutectic structures is the lamella structure, right? A layer structure. Of course, there are different microstructure of this eutectic structure, such as the needle-like flat plates in aluminum silicon alloy. Okay, so I just want to tell you that there are different microstructure for the eutectic. Okay. Oh, it's some SCN microscope shows that the needle-like silicon plates in aluminum silicon eutectic. So this is the needle. This is the needle, and this is the needle. Okay, so and this is the silicon, and this is the aluminum and silicon alloy. Okay, and for the figure B shows the rounded silicon rod. This is silicon, and modify the aluminum silicon eutectic. Okay, so there are some dendrites in this, microstructure. Okay, some dendritic growth the structure. Okay, so you can see there's some dendrite here, okay, here. Oh, maybe it's not quite clear, but we can see that. Okay, so this dendrite structure. Okay, this dendrite structure, or this dendritic growth, to be grown into the thin interconnected rods, and this growth, this dendritic growth, increases the tensile stress and the percent elongation. Wow, so it's quite amazing because this kind of structure can increase the mechanical strength and the elongation. Usually, these two types of mechanical properties, tensile stress and the elongation. Well, suddenly, these two types of mechanical properties will not enhance simultaneously in the same condition. Okay. Okay, so the eutectics and materials processing, manufacturing processing often take advantage of the lower melting temperature associated with the eutectic reaction. So if we can look at this phase diagram like this. If we can look at the phase diagram like this, what we can figure out is that at this point, this eutectic reaction, it has the lowest melting temperature, right? This is the eutectic reaction. Its melting point is 183, right? If we choose a different composition, say 40 weight per self-tin, right? What's its melting temperature? Well, it's right here. It's about 240, right? This may be 240, and it's 183. So why not? Why not? We just specify the composition of the eutectic reaction, because at this composition, its melting temperature is the lowest and its mechanical strength is highest, right? Okay, so the casting alloys, such as the casting iron or aluminum alloys, are based on the eutectic alloy. So why? Why this casting alloy are based on the eutectic alloys? Why? For the casting, we have to control the viscosity of this liquid metal, right? Control the liquid phase. If we choose the different composition, when choose the hypo or hyper eutectic composition, what's going to happen for the casting process? While this liquid may not flow through this pattern, this whole mold that you design. Okay, you know what I'm saying? Okay, if you choose the hypo, that means we have the two-phase region, right? Okay, let's look at this figure again. So for the casting, we have to specify the composition at the eutectic reaction because its melting temperature is the lowest. Okay, if we don't choose this eutectic composition, say for example we get it this 40% of tin as the casting alloy, what's going to happen? We have to heat up at higher melting temperature, right? And when we pour this liquid into the mold, and when this temperature cools to this two-phase region, say at this point, and its viscosity change. Okay, its viscosity change. Its viscosity is getting higher and higher. That means it's not easy to flow through the pattern of the mold you design. Right? So if you choose this composition, say 40 weight% of tin as the casting alloy, when you pour this this liquid into your mold, and when you open up the mold, you will find out that this figure, this structure, this figure or structure is not what you want. It's not what you design. Okay, so the same thing will happen if you choose the composition is the hyper eutectic. Okay, therefore we say the casting alloys are based on the eutectic alloy. And also the eutectic alloys such as tin, lead are used for soldering, okay, during assembly parts, because the similar idea is that we can melt this solder at the lowest temperature and provide the highest mechanical property. Okay, and eutectics are also important in many ceramic systems, such as silica and aluminum. So this eutectic reaction is not only for metal, but also the ceramic system. Okay, so we can find out, okay, it's the liquid phase, ceramics phase, liquid ceramics transfer to two solid ceramics. Okay, therefore the eutectics are also important in ceramic system, right? So we can get the lowest temperature of this ceramics compound, right? And its mechanical properties are highest for this ceramic component, right? So our course will be ended here. So see you next time.